Let's talk about security and observing security. This is an interesting report from the network service provider Verizon. They produce an annual report on data breach investigations, particularly targeted at networks. So in this particular report, they talk about breach patterns shifting towards vulnerability exploitation and a sharp rise in third-party involvement, underscoring the need for continuous visibility across internal systems and supply chains. That's one of the key weaknesses in security. You need to make sure that you've got security end-to-end across both development and suppliers to development, different components, as well as into production. Mandiant M Trends 25, this is a report, visualizes dwell time, showing that incidents detected internally have a median of approximately 10 days compared to 26 days when discovered by external parties. But this directly supports the need for richer internal telemetry and detection coverage. There's a big gap there from a security point of view. Okay, this term EBPF, you may not be familiar with. It stands for Extended Berkeley Packet Filter. It's a little tool inside Linux kernels. It was originally created for packet filtering, but it can be used for other things with security. So the revolutionary technology with origins in the Linux kernel can run sandbox programs in a privileged context, such as the operating system kernel. So it can be used for observability, security controls, network security, and load balancing. The diagram pretty much says the same thing. This little diagram on the right shows how it's embedded in the kernel, and it can be used to implement stack traces inside the kernel and also monitor processes that are supported by the kernel, the Linux kernel. EBPF can also help build service maps. So if tracing cannot be added to the code, it's possible to detect network traffic at a lower level, at the kernel level. eBPF is a technology for tapping into operating system calls that can be used to detect and report connections. So this is just a statement of the same thing, a little flowchart. If tracing is not possible, use eBPF to detect connections. This is an example of an actual service chart that can be produced with eBPF. So you can see relationships, for example, the kubelet, Kubernetes instance could be mapped to metric servers, core DNS, which in turn could be mapped to the front end and different sessions. Those in turn could be mapped to API servers. So again, it's just a way to help map out the different connections, understand the relationships between different components, which then indeed can tell you something about concerns and vulnerabilities. This is a way of observing security with eBPF. There's another tool called BCC. It's a set of tools. This really stands for eBPF, compiler collection. So it's a collection tool that's tied to eBPF. It makes it easier to write, compile, and run eBPF programs. So BCC is a toolkit for creating efficient kernel tracing and manipulation programs. It makes BPF programs easier to write, suited for many tasks, including performance analysis and network traffic control. This diagram, pretty complicated looking diagram, talks about where you can inject some tracing tools all the way from the driver level, memory level, schedulers, different parts of the kernel, system calls, system libraries, runtimes, and applications. I don't think I'll go through all of those details. You can study it on your own if you like. But fundamentally, it does show you there are ways to get access and visibility, observability, in other words, pretty much through all parts of the kernel. So talking about the security software delivery cycle with observability, so if you want to validate the use of ephemeral infrastructures that protects builds from cache poisoning, monitoring SBOMs, software bill of materials generation and distribution to consumers so that they can verify the dependency chain for new vulnerabilities. Inspect intrusion detection on bill servers, scan open source libraries, scan system packages, check and scan the build scripts, scan Git, code version repositories, scan container images and container registries. So there's a lot of scanning going on in a typical, DevSecOps continuous delivery cycle. Observability tools can help reinforce security in the software supply chain by providing visibility. And you can also request your vendors that are supplying code to run these checks prior to even delivering their components to you. That's a pretty good idea, typical best practice. Let's talk about container security in particular. So the vulnerabilities, first of all, I hope you know what a vulnerability is, but there's a definition here. It's a known software defect that a potential attacker can take advantage of to execute some malicious code or malicious activity. So this can apply to container images, patches, distributions, application libraries that you might import. And a security event corresponds to any identifiable occurrence that has significance for any piece of the platform, indicating that a security policy has been violated. This can again apply to container logs, the RBAC policies, the admission controls, container runtime. So a container is a standard unit of software that packages up code with all its dependencies so the application can run quickly and reliably from one computing environment to another. So that's basically just a few definitions regarding vulnerabilities and events in containers. There's plenty of risks around, containers and images. So the image risks may include vulnerabilities in the image, configuration of the container, defects, embedded malware, embedded clear text secrets, and use of untrusted images are kind of typical vulnerabilities that can occur. And also registry risks. So you could have insecure connections to registries, stale images in registries, insufficient authentication and authorization restrictions. You can also have orchestrator risks, so things like Kubernetes orchestrators, unbounded, administration access, unauthorized access, poorly separated inter-container network traffic, mixing of workload sensitivity levels, and orchestration node trust is another type of risk. Another type of risk in the container itself, vulnerabilities within the runtime environment, unbounded network access from containers, insecure container runtime configurations, and app vulnerabilities and rogue containers. And last but not least, host operating system risks, large attack surfaces, shared kernel, host OS and component vulnerabilities, improper user access rights, and host operating system file system tampering. So again, these are the diagram just says the same thing, some of the risks associated with containers.